Welcome back, folks, and getting into chapter 3 here, we're going to take a look at fatty acids. Now, you've probably noticed we've not covered nucleic acids or carbohydrates in this chapter. I'm going to leave those to your own readings and make sure again you focus on the important principles and focus on the new material. So fatty acids, let's get into fatty acids and do a quick review of that, and then look at a little bit of new material, some variations on fatty acid derivatives and phospholipid derivatives. So fatty acids are used to build several other kinds of lipid, and so lipid is the general category. Fatty acid is a kind of lipid, and so some people say that fatty acids are amphipathic. They're these long hydrocarbon chains, and because they've got this carboxylic acid group on one end, these carboxylic acid groups here, because we've got those carboxylic acid groups, some people describe fatty acids as being hydrophilic. My feeling is that group is not sufficiently large and polar for it to be considered amphipathic, but I know that some people certainly say that molecule is amphipathic. I would say it's predominantly hydrophobic. But that discussion aside, we have an acidic carboxylic acid group, so they can donate a proton to solution to become COO-, and then we have a long fatty acid chain. And the chain lengths are variable, and they range from about 12 to 20 carbons in length. You often find, you're more likely to find even numbers of carbons in the tails, or in the fatty acids, and that's because fatty acids are grown and shrunk by 2 carbon increments, and so you take off 2 carbons, you add 2 carbons at a time, and because you start with an even number, you often see even number carbon length fatty acids. So these are obviously highly reduced molecules, tons and tons of hydrogen associated with the carbon backbone, and so they store a large amount of chemical potential energy. When we oxidize them, we can liberate that chemical potential energy, and we can then convert that chemical potential energy into another form of chemical potential energy, obviously in the bonds of the molecule adenosine triphosphate. Now, when we have saturated fatty acids, every single carbon in the chain is making the maximum number of bonds to hydrogen. So for most carbons, all carbons in that chain, it's 2 bonds with hydrogen. No, we're not talking about hydrogen bonds, but bonds made to hydrogen from carbon. The exception to that is the end carbon here or here, and that'll obviously be making 3 bonds with hydrogens, so that the octet rule is satisfied. And if we look at unsaturated fatty acids can have a double bond introduced. So there, at the point of the double bond, these 2 carbons which flank the double bond are only making 1 bond with a hydrogen, and when that double bond is in the cis conformation, we get a very dramatic bend in the fatty acid, and that changes the structure, and therefore we see some effects on the chemical properties and therefore the functions of these kinds of fatty acids. So these fatty acids on the left will be tightly packed. They form solid types of fats, generally classified as fats, and these unsaturated fatty acids will generally form oils at room temperature. Now, we can take fatty acids and we can link them to a glycerol molecule. We do 3 condensation reactions, 3 water molecules produced. We link 3 fatty acids to glycerols, and we can end up producing this molecule here, a triacyl glycerol, and so that is a energy storage molecule. That's what you find in adipocytes, and that's what we're going to break down if we're going to be able to burn fat. Let's kind of look at some variations of this. So you're probably familiar with phospholipids, where 2 fatty acids are esterified to a glycerol, and then we have a phosphate group attached to the glycerol at one end, and then there are often a number of small hydrophilic groups added at the R position here to form phosphoglycerides, what we know as phospholipids, and that R group there can change, and we'll take a look at some of the variations when we look at phospholipids and membrane structure in more detail. Sphingolipids, we're going to use a variation of glycerol, and with one fatty acid attached we have sphingosine, and then we use an amide linkage to attach another fatty acid, and we have a phosphate attached to a hydrophilic R group, and this is now known as a sphingolipid. So that's a variation on a phospholipid, and you find these sphingolipids in membranes also. Down here we're looking at glycolipid, and the glycolipid is a sphingosine, except there is no phosphate attached here. Is what we see here instead is the R position would be a carbohydrate chain, and so there's been a carbohydrate added to this sphingosine molecule, and that gives us a glycolipid. And we're not going to touch on steroids and terpenes here, but you should remember the steroids, a form of lipid, and you may not have encountered terpenes before. So here's isoprene. Isoprene is a basic fatty building block of molecules such as vitamin A, which is a fat-soluble vitamin. And you can see the terpene repeating units here, making up the tail of this vitamin A molecule. So some variations on that. Let's return to fatty acids and saturation. So remember that when we're dealing with a saturated fatty acid, every single carbon in the chain over here on the left is forming the maximum number of bonds to hydrogen atoms, and so this is saturated with hydrogen, and so the fatty acid, such as palmitate, is saturated. Now over on the right we've introduced a cis double bond. The two hydrogens are in the cis conformation, they're on the same side as one another, and so that introduces this double bond, and that significantly changes the characteristics, the chemical characteristics of the molecule, the structural characteristics of the molecule. Oleate, found in high concentrations in olive oil, is not going to pack tightly with its neighboring fatty acids, with its neighboring oleate molecules, and so it's going to form a liquid at room temperature. So you are going to find trans double bonds as well, so you will hear about trans fats. They're pretty rare in nature. You don't find them commonly in cells, but they're made artificially when people do things like make margarines and that kind of stuff. And those are the kinds of fats, which are the bad fats, which are associated with heart disease and that kind of thing. So let's kind of now turn our attention to phospholipids a little bit. We started off looking at this basic phosphoglyceride, this basic phospholipid here. This is phosphatidic acid, and it's the basic building block of all phospholipids. So you've got the familiar glycerol here, and then we've got two fatty acids esterified to the glycerol, and then we've got a phosphate group, and then there will be some other R group here. And that can be as simple as a hydroxyl group, in which case this becomes phosphatidic acid. Phosphatidic acid is rare in membranes. It's not a common phospholipid seen in membranes, but it's a basic building block, and we just substitute out the R group when we need to. So we can put in this R position any number of small hydrophilic alcohols, things like serine, ethanolamine, choline, or even the more complicated inositol. And so we could end up with phosphatidyl-serine, phosphatidyl-ethanolamine, phosphatidyl-choline, phosphatidyl-inositol. And so we can make lots of different types of phospholipid based on this variable R group that we can put different substituents into. So we'll talk more about these and their functions when we get into to looking at membrane structure and membrane function a little bit later. We can also then think about the sphingolipids once more, and so here's our basic phosphoglyceride, the glycerol here shaded, the phosphate group and an R group. This would be phosphatidic acid, change the R to serine, and that's phosphatidylserine. With a sphingolipid we have a sphingosine, which is this molecule shaded in yellow here, and so the important thing is here we're going to stick on an amide linkage to another fatty acid, and you can see there's some slight differences up here between sphingosine and glycerol, and then we can again have some variability in the R group. So those are sphingosines compared to phosphoglycerides. And then lastly, if we take this R group and we make it a lipid, and we have, if we make it a carbohydrate, if we make the R group a carbohydrate and we attach that to this sphingosine with another fatty acid connected with this amide linkage right in here, then we end up with a glycolipid. And so these glycolipids they're largely in the outer membrane of the plasma membrane. And that sugar can be glucose, galactose, N-acetyl D-galactosamine, so all kinds of different sugars that you'll see associated with these glycolipids. And we'll talk more about the synthesis of these and their functions when we talk about membrane structure and function a little bit later. So that's just a real quick run through on fatty acids, building up through phospholipids, sphingosine, glycolipids, and those last two are kind of variations on the common phospholipids that you'll be familiar with from general biology. So that's it. Next time we're going to start getting into chapter 4. I'll see you soon.